Okay, Matt Roscoe here at the University of Montana with a short video to finish out our treatment of Chapter 6.1 from Burton's text on number theoretic functions, tau and sigma. We've gotten through most of this chapter in class, but I had just a little bit left. Remember that when we left off, we determined that there was actually a closed form for computing both tau of n and sigma of n for any number that has a unique prime factorization. So I guess this means any integer greater than 1. And we didn't prove the tau of n, but we did prove the sigma n proof. And I believe we got to this spot where we took a look at computing these for tau and sigma of n. So we finished off with this. And this was an intended I guess results. So maybe we should just go back and make sure that we're clear here because it's meant to sort of front load the next chapter. Let's go ahead and get a live picture here. So our example would have been, if we're given an n and the n's provided were 16, 15, and 240, then what is sigma of n? What is tau of n for each of these? So let's go ahead and just find out. Let's start out with 16. So if n is equal to 16, well, we know that then 16 is the same thing as 2 to the 4th. So we can simply compute it now using the closed forms. Sigma of n is going to be equal to the exponent 4 plus a 1 times no other exponents, plus 1. So I guess sigma of n is just going to be 5. So 16's number of factors are 5, and they're exactly the powers of 2 if you include 2 to the 0. And then how about tau of n? So tau of n is going to have just one rational argument. It'll be 1 minus 2 raised to the 4 plus 1 all over 1 minus 2. So let's just see here. That's going to be 1 minus 2 to the 5th all over negative 1. See, 2 to the 5th is 32, so 1 minus 32 is negative 31 all over negative 1. So that leaves, I guess, a positive 31 as our tau of n. If we take a look at 16, the question is, how have we checked this? So to check it, what I would do is look at the factors of 16 and just add them together. Let's see, so the factors of 16 are 1 and 16, 2 and 8, 4 and 4, and that's it. So what I would do is add 1 plus 2 plus 4 just once, because it's a factor only once, 8 plus 16. I can see this is 16 plus 8 is going to be 24, plus 4 more is 28, 29, 30, 31, right? So this is indeed 31, so it does check. Let's take a look at 15 now. If n is equal to 15, what do we get? Well, 15 is just a 3 to the first times a 5 to the first. I put the firsts up there because, of course, they're helpful in computing sigma of n, which is just going to be 1 plus 1 for that exponent times a 1 plus a 1 for that exponent. So what do we get here? We get 2 times 2 or 4. And then let's see, tau of n is going to be two rational arguments. It's going to be 1 minus 3 raised to the 1 plus 1 all over 1 minus 3. And then that is going to be multiplied by 1 minus 5 raised to the 1 plus 1 all over 1 minus 5. So let's see, what do we get here? We get 1 minus 3 squared. 3 squared is 9, so we'd have negative 8 all over negative 2. And here we'd have 5 squared is 25. 1 minus 25 would be negative 24 all over negative 4. So what do we get? We get 4 times 6, or 24 here as our answer. So once again, 4 and 24 as our answers there. let's go ahead and tear off another sheet. I'll make sure and make this into a PDF and make it available to you. I hope you can read it fairly good on the video. Let's try one more. Let's let n be equal to 240. So let's just see how that works out. So 240, of course, is a much bigger number. We should expect both sigma of n and tau of n to perhaps be bigger. It looks to be heavily composite. It's divisible by at least 2 and 5, and it looks like 4 and 24 is visible by a whole bunch of things like 8, 4, 12. So let's go ahead and if we were to decompose this in its prime factors, we would get 2 to the 4th times 3 to the 1st times 5 to the 1st. So that makes it fairly straightforward then to calculate sigma of n. That's going to just be a 4 plus a 1 times a 1 plus a 1 times a 1 plus a 1. So it's 5 times 2 times 2. So that's 10 times 2 or 20. So apparently this number has a total of 20 factors. We didn't find them. We just used theory, of course, to predict how many. Tau of n will now have 3 rational expressions. It'll be 1 minus 2 to the 4 plus 1 all over 1 minus 2. That will be multiplied by 1 minus 3 to the 1 plus 1 all over 1 minus 3. And that'll be multiplied by 1 minus 5 to the 1 plus 1 all over 1 minus 5. So what do we get? We get 1 minus 2 to the 5th all over negative 1. 2 to the 5th is 32, so it's negative 31 over negative 1. 1 minus 3 squared all over 2, so again it's going to be negative 8 all over negative 2. And then the 5, 1 minus 5 squared is going to be 24 negative all over negative 4. And I don't know if you're noticing this, but there's some numbers that we're sort of familiar with, right? The 31 and the 8, 2, and 24. So it looks like it's 31 times 4 times 6. So here we get 744 as the sum of all the factors of 240. So 20 and 744. So this was trying to front load the next topic in our chapter, and that's this unique thing. I don't know if you noticed, but if you take 15 times 16, you actually get 240. And if you take tau of n times tau of n for 16 and 15, you get tau of n for 240. And this one might need to be checked, but you can kind of see that, well, seems like it might be a product as well. 31 times 24. Is that indeed 744? Well, let's just try it out. 31 times 24 is 744. So what it seems to mean is that, if you know tau of n for small numbers, you can multiply these things up to find tau of n and sigma n for large numbers. And so this makes it kind of interesting because if you know small, you can predict, I guess, products of a number, what their sigma and tau n are simply by multiplying up those sort of sub values for their factors. And that's literally the next slide here. We say that, we define this much larger than just tau and sigma. We just define it for all functions, and we say that a number theoretic function f is said to be multiplicative if the value of the function for a product m and n is equal to the value of the function for each of its subsequent factors. So f of m times f of n. And that's only good when the GCD of m and n is equal to 1. So I don't know if you noticed this, but in our example we had 15 and 16 as our m and n, and both 15 and 16 share no factors. That's a definition, and what it appears is that both tau and sigma are multiplicative functions. I mean, at least that's what one example showed us. So we should probably, sorry about that, we should probably prove this, at least one of these two statements. So let's go ahead and switch over here to the live image. And and prove it. First maybe I would say is that there is an advantage of multiplicative functions, and that is this, that if you know some function can be written as p1 to the k1 times p2 to the k2 times all the way up to, let's say, pr to the kr, then if we take some multiplicative function f of this number, that's the same thing as f of p1 to the k1, p2 to the k2, all the way up to pr to the kr. Well, if it's multiplicative, then the idea is that that this thing can always be written this way, p1 to the k1 times f of p2 to the k2, oops, times all the way up to f of the pr to the kr. And you can always do this, I should say f is multiplicative. And you can always do this because the GCD of any two prime numbers, because none of these primes are repeated in a prime factorization, so the GCD of, say, pi, pj has got to be 1 for I not equal to j. So that's kind of interesting. I mean, right away we know that if you know a number's prime factorization, you can sort of break down the application of the function to its application to each of its prime factors. You should also note, so I would say note 1, that's note 1. Now let's take a look at another kind of an interesting note. So note 2, if f is multiplicative, let's see, with some value n such that f of n is not equal to 0. So it's if there's just at least one n where it's a non-zero function, then it forces the function's value at 1 to be equal to 1. So off we go here. The proof here is fairly straightforward. If f is multiplicative, then f of n is certainly equal to f of n times 1. I mean, n and n times 1 are the same thing. If it's multiplicative, then f of n times f of 1 should be able to be computed. And if f of n is non-zero, then we can divide it through on both sides. And what do we get? We get out here that f of 1, which is f of n over f of n, has to be equal to 1. So anytime we have a non-zero valued function, in other words, where there's at least one value of n in the naturals that is non-zero, then it forces the value at 1 for the function to be equal to 1. Small footnote here. All right. So having taken care of a few notes, let's prove that tau of n. I'll let sigma n be multiplicative. I'll let you read that proof in the book, but let's go ahead and prove that tau of n is multiplicative. So let's see. Here's our hypothesis. Tau of n is multiplicative. And here is our proof. I'm noticing a lot of shadow. I'm going to pause here for a second and put my window shade down. Okay, that looks a little better. Let's see, here's our proof. First of all, we have to let m and n be relatively prime. integers. And then say, well, if either m or m are 1, then it's trivial, right? And the result is trivial for m n equal to 1. So assume that m is greater than 1 and n is greater than 1. So then what do we have? Let's see. Well, then m has some prime factorization. It's p1 to the k1 times p2 to the k2. Let's say all the way up to pr to the k r. And n will indeed have prime factorization different, potentially different. q1, let's say to the j1 times q2 to the j2 all the way up to, say, q. It can't be the same index as r, so we'll have to use s to the js. So again, they each have a unique prime factorization. So we'll say these are the prime factorizations of m and n. Now, because the GCD of m and n is equal to 1, no pi, let's say, is equal to any q. I don't know, let's say, I don't want to use j's, any q, k, I guess, for what I, 1 to r, and I guess k in 1 to s. So none of these q's are equal to any of these p's, and vice versa. So what can we write? When we do mn, literally all you're doing is smushing these two prime factorizations together with no overlap because of the GCD restriction. So it must be p1 k1 times p2 k2 times all the way up to pr kr, and then times q1 j1 q2 j2 all the way up to qs js. And thus, what does tau then of mn look like? Well, tau looks like this k1 plus 1 times this k2 plus 1 times all of these in the middle, plus this last kr plus 1 times the j1 plus 1 times the j2 plus 1 times all the ones in the middle times the js plus 1, right? So here we can just see that this thing right here is the same thing as tau of m, and this thing right here is the same thing as tau of n. And that's what we wanted to show. So ends the proof. Now, I guess what I would tell you is that if you're thinking about what to do with sigma n, sigma n is going to be, the proof for sigma n is going to be very similar to this. I mean, you're going to get to the same spot as right here and then apply the function sigma n to this longer prime factorization. And of course, the first chunk will be recognizable as sigma of m, and the second chunk would be recognizable as sigma of n. So it's a very similar proof for sigma of n being multiplicative. as tau of n being multiplicative. There is a couple neat lemmas to this. Here's the first lemma, that if the GCD of M and N is 1, the set of positive divisors of M and N consists of all products D1 times D2, where D1 divides M and D2 divides N, and the GCD of D1 and D2 is 1, and all of these products are then distinct. So kind of an interesting idea. Maybe I won't provide the proof of this. The proof is in the book, but maybe we should use this lemma to get a sense of what it means. But it sounds like the set of positive divisors of a product where the two factors in the product share no factors is the set of all possible, I guess, cross products is sort of the way we think of this, of the divisors for each of them, where each of these divisors share no factors. So let's take a look at how that looks in an example. Let's see here. Here it is, live image. So let's take two numbers, let's say like m equal to 21, which is the same thing as 3 to the first times 7 to the first, and n equal to 25, which is the same thing as 5 squared. And let's just see here. If we compute mn, just to get a sense of what that is, 21 times 25, 525. So the idea is that we can find all the divisors of 525 by finding all the products of the divisors of these two numbers, which are relatively prime. So 21's divisors are, of course, there's going to be 4 of them, I can tell. So it's 1, 3, 7, and 21. And 25's and divisors. Let's see, so it's 2, 3 of them. So 1, 5, and 25. So you can kind of think of it this way. We just need to compute all the products of these two lists. If we put the, I guess, 21's divisors across the top, 1, 3, 7, and 21. If we put 25's down the side, 1, 5, and 25. Then the products here are 1, 3, 7, 21, 5, and 25. Well, certainly these ones will divide 525 because it's a product of those two things. But kind of interestingly are these ones in the middle, 15, 35, 105, 75, 175, and 525. So there they are. I mean, some things to notice is that, all of these are distinct. We actually never get one that repeats. Of course, they're all positive because we've chosen all the positive factors or divisors. And these are all the divisors of 525. If you kind of think about it, if n is equal to 525, which is going to be 3 to the first times 7 to the first times 5 squared, then tau of n is going to be 2 times 2 times 3. So it's 4 times 3 or 12. And indeed, these are the 12 factors of 525. So a quick example, I guess, of the lemma. I would ask you to take a look at the proof in the book. One last theorem is that if f is a multiplicative function, then this big function we call f, which is a sum of the results of the multiplicative function f applied to the divisors of n is also multiplicative. So anytime we make a sum of the results, I guess, of a multiplicative function for certain divisors of a number, then that is also multiplicative. I think this is kind of an interesting sort of large scale idea here. So let's take some time and pick this apart a bit. Why does this happen, right? So I'll go ahead and switch over to my So let's go ahead and prove that. So I'll let the hypothesis be on the slide. Here is our proof. Let's let m and n be relatively prime integers that are positive. Valued. Then if f of m n will be some sum of any across any divisor of m times n applied to f. Okay, so let's see. So this thing, it turns out we can use our previous result. If both m and n are split up and m and m are relatively prime, then we can simply sum across the divisors of m and n individually, right? Because every divisor of m and n is some product of the two of a divisor of m or a divisor of n, which is sort of what we just saw here, right? Every factor of 525 is some product of the divisors of 21 and 25, which are both relatively prime. Okay, so let's keep moving here. So, let's see, because every divisor of mn can be uniquely written as a product of a divisor, we'll call it d1 of m, and a divisor Well, I had a little technical glitch there. My screen froze. Sometimes my Elmo Cam does this. So it looked like I got to about right here. So I'll go ahead and walk through the rest of this with you. So we get to this spot where we use the result from our previous lemma to say that the function evaluated d could be seen as the function evaluated for every d that divides m and every d2 that divides n. And of course, d1 and d2 have to be relatively prime since they're divisors of two numbers that are relatively prime. So since f is then multiplicative, we can kind of consider this f of d, which we've rewritten as f of d1 times d2, to be the product of the function evaluated for d1 and evaluated for d2. This, of course, is the definition of a multiplicative function, so we're simply applying it here, and f is known to be multiplicative in that's one of the givens in the proof. And here's where it gets fun. So if we can rewrite this piece as this product, we can think of this as, well, this is just the sum for all d1s dividing m and all d2s dividing n of the product of f of d1 times the times f of d2. And ultimately what we want to show is that, we'd like to show that this part right here is f of m and this part right here is f of n, and we can do so if we can break the sum out across both. And indeed you can. It turns out that this is equal to this, and I think that an example might help you see it a little bit better. But the idea is that the product of all these can actually be factored into the sum of all the divisors of m1 evaluated for f of d1 times the sum of all the divisors for n2 evaluated for f of d2. And once we get to that stage, then we can recognize that indeed this guy is that's just f of n, right? Divisors of n, f of n. Well, that's what I guess big F is defined as. And again, f of m here, all the divisors of n evaluated in some multiplicative function. So indeed, big F is multiplicative. Let's just take a quick example to show you this starred step here. So for example, what if we were looking at f of 24, right? Well, that's the same thing as f of 8 times 3, and sorry, I'm not little f, I want big F, right? And the question is this thing equal to f of 8 times f of 3, right? So that's the big question mark. So let's just take a look at f of 8 times 3. So what do we get? Well, that's just the sum of all divisors of 24 evaluated for some generic, let's say, number theoretic function f of d. So what are those things? I'm going to need some space here. This is a wide thing. All the divisors of 24, well, that means it's f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 6 is a divisor of 24, and then f of 8, plus f of 12 plus f of 24. So all the divisors of 24 are evaluated for this function. So now just think about, well, how could I use 8 and 3 to rewrite each one of these? This guy would be f of 1 times 1, right? Both factors of 8. This would be f of Well, I had a little bit of a screen freeze here again, so I'll catch you back up. So all we've done is we've summed the function across the divisors of 24. We've written each divisor of 24 as a product of one of the divisors of 8 and 3 here. And then in this next line, what I've done is I've applied what I know about f being multiplicative to say that f of a product would be the product of the function evaluated at each one of the factors. So 1 times 1 can be written as f of 1 times f of 1. 1 times 2 can be written as f of 1 times f of 2. 1, 3, 1, 4. So here's 6 would be 3 times 2. Trying to keep track here of my addition and multiplication. Of course, the two functions whose product is being evaluated are multiplied, and then there's an addition for each value of the function. So at this point, I notice that what I'm trying to do is show that this is just f of, big F of the factors of 8 times big F of the factors of 3. And it's easiest to pull out the factors of 3. The factors of 3, of course, are 1 and 3. So I'll highlight every value that has a 1 here. Here's a 1, here's a 1, here's a 1, here's a 1. And here's a 1. So those all have a 1 in them. And then I'll pull out all the ones that have a factor of 3. So here's a 3, here's a 3, here's a 3, and here's a 3. So if I do that, I have to do a little rearranging, but let's see, did I get them all? I think I did. So if I pull out the f of 1's, what do I get left inside? Well, I get f of 1 plus f of 2. Let's see, it's 1, 2. I'm going to leave this one because it has both of them in it. F of 1, oh, f of 4, sorry. That's from here. And f of 8. Okay, that's the one that has all the 1's in it. And then if I pull all of the 3's out, let's see what I get there. So f of 3 in this one, so it'll have a, oh, I should, f of 1 plus f of 2, there it is, plus f of 4 plus f of 8. And what I notice is that what's in square brackets is exactly the same. So when I pull the square brackets out in front, I get, I guess it's f of 1 plus f of 2 plus f of 4 plus f of 8. And what I guess would be left inside, let's say curly brackets, it would be f of 1 plus f of 3. And of course this is recognizable as just big F of 8. Those are all the divisors of 8. And this is just big F of 3. I don't know if that helps you understand that a little bit better, but the idea is that anytime I have something written here as the product through algebra, I guess, it can be simplified to the product of two sums, each for the individual factors involved. That, in effect, exemplifies this jump right here, where we have the product of two factors can be thought of as separate sums of the product of separate sums of each of the factors of the two numbers. I hope that makes sense. And that's really it for this particular chapter. And we'll move on to take a look at chapter 6-2 next.